Hello everyone and welcome to the new lecture. And today we will going to continue our discussion on this canonical transformation. So if you remember, we have done some examples, and then we'll continue to infinitesimal canonical transformation, and based on that we did some discussion and some calculations. And now today we will move to a part of that Hamilton-Jacobi theory, which we had already discussed. That what is the aim of that Hamilton-Jacobi theory is that we had already gone through this Lagrangian to Hamiltonian formalism, in which my Lagrangian the dependent part of the Lagrangian, basically the coordinate, generalized coordinate, and the generalized velocity. When your generalized velocity is transformed to the generalized momenta, then you have from Lagrangian formalism to the Hamiltonian formalism in the phase space. Okay, that this is what we do. Then we have this canonical transformation for in which your old coordinate, you transform your old canonical variables small qp to large QP, that is the new canonical variables, demanding that the Hamilton canonical equation preserves, and then the modified Hamilton principle also remains same. So with that, we discussed that infinitesimal canonical transformation, that is in terms of when the generator of that infinitesimal transformation is Hamiltonian, that gives you the translation of the system in space, and then their corresponding conservation theorems of linear momenta and angular momenta. So Hamilton-Jacobi theory basically aims to simplify the canonical Hamilton equations of motion. That you can see that in Hamilton equation, I have q dot and p dot, that can be calculated in terms of the partial derivative of the Hamiltonian corresponding to momenta and the coordinate. So we are going to, when you go from Lagrangian formalism to Hamiltonian formalism, you have seen that you go from the second order differential equation to the first order differential equation, but the number of the differential equation increases by twofold. So there you have n number of, in Lagrangian formalism you have n number of second order differential equation, and because you know that in Lagrangian equations of motion, what you have is d dt of delta L by q dot. You have q dot here, and then you have delta L upon delta q equal to 0. So from here you have second order differential equation, and that these numbers are going to be n numbers of, depending upon the what number of generalized coordinates you have, dependent on the Lagrangian depends on. And then when you move from this Lagrangian to Hamiltonian formalism, you have simplified by demanding certain conditions to be canonical, that your equations of motion from the second order to become these two first order. So from n number, you have n for this and n for this. Now you have 2n number of differential equations, but because these are the first order differential equations, so solving this is going to be easier. So that was the benefit of transforming from Lagrangian formalism to the Hamiltonian formalism. Continuing this in terms of the canonical transformation, the Hamilton-Jacobi theory aims to simplify further the solving of these differential equation by finding a single function, and if you have that single function, then you have some derivative based on that function that contains the information about the entire dynamics of the system. So this is what Hamilton-Jacobi theory is aiming for. So, so let's discuss about this goal of the Hamilton-Jacobi theory is that, so when you seek a canonical transformation from your old variables qp to the new variable qp, such that the new Hamiltonian, if you remember, k becomes as simple as possible. Because when you remember that in your canonical transformation, that your Hamiltonian, the old Hamiltonian, that is p q dot minus L, or say this Hamilton equation, Hamilton principle is like this is p q dot minus h, and then this new Hamiltonian is my k and then you have part of generating function is equal to 0. Okay, so this gives you the generating function, which, if you remember, this is where you have some lambda multiplicative constant when you transform from this qp to some qp. Okay, this is what you do in canonical transformation, demanding that the new Hamiltonian is cyclic in the coordinate. So in Hamilton-Jacobi theory, what you demand is that my new Hamiltonian K is going to be as simple as possible, because when you transform canonically your canonical variables small qp to new qp, the capital qp, then you demand that the Hamiltonian is now as simple as, and the simplest form of your new Hamiltonian form using the new canonical variable is going to be either it is equal to 0 or it is equal to some constant. Okay, so when you demand this in Hamilton-Jacobi theory, that then this gives you that the new momenta pi and the coordinates qi, this capital momenta pi and qi, become constant, because when you see that from the Hamilton equations of motion, when you new Hamiltonian k, then your Hamilton equations of motions are going to be this q dot and p dot, that is going to be delta k upon delta pi, delta k upon delta qi. So these are because we demand that this k, the new Hamiltonian, is going to be 0, either 0 or constant, to be as simple as possible. Then these things are going to be constant. So that is my dq by dt is that is going to be 0. So that implies that q is constant, and so from here p is constant. So when we demand that, then this tells me that this momentum pi and the coordinate qi becomes constant. That is the system is being solved when coordinates in the moment are constant, and then q dot and p dot is going to be 0. So then you can integrate and you can find the time dependence from that, because this is dq by dt. You integrate and then you find how the dependence on time is there. So you solve the equation. So it means that what we seek a canonical transformation from the small coordinates qp, that is my old canonical variables, at the time t, to a new set of constant quantities, that is going to be capital qp, which may be 2n initial values at time t equal to 0, because when we have at time t equal to 0, because when you have a constant, you need some initial conditions to solve your problems. So that initial conditions values are going to be 2n, because you have 2n differential equation at time t equal to 0, and then as the system moves from time t equal to 0 to certain time t, and then you transform that variable small qp to a new canonical variable capital qp. So Jacobi provides a method which is a transformation which is applicable when your Hamiltonian involves time. This is important, that in Hamilton-Jacobi theorem or in Hamilton-Jacobi formulas or method, whatever you say, is a transformation that has to be canonical, and it is applicable when your Hamiltonian involves a time, and all coordinates and momenta are going to be cyclic in that case, because then cyclic, you know that is those variables, the coordinates and momenta, are going to be corresponding momenta are going to be constant. So that's why it is going to be the cyclic. So what we are going to do, that the new Hamiltonian, which is my k, depends upon the new variables capital q, p and t, is related to the original Hamiltonian old one, which we know that this is what the relation is from the canonical variable, as you can see from here. So this is what we seek, and then if this is happening, then what I'm demanding in Hamilton-Jacobi theory, that this has to be, because this we need to be equal to 0. Okay, so when this is equal to 0, then f satisfy this this, we have this relation that h plus time derivative of partial time derivative of your f is going to be 0. So you will see that f is here is generating function. So whenever you are doing a certain transformation, you need a generating function. If transforming from one coordinates to to second, that you need a transformation equation, and to that generate that transformation, you need that generator of that. So f is playing a role here. So here also we are transforming, so we need a generator, and what the generator is going to be. So you may choose any of the four kind, because you see that in canonical transformation you have existing four type of generator is available. So then you can choose any of them. So for this time, let us consider the generating function of the canonical transformation. We say type 2, say f2. So type 2 is f2, and you see when that it depends upon a small q and capital P and T. Okay, this is my type 2 generating function. Okay, so then with its derivative and satisfying, so when you have type 2 generating function, and you know that every generating function has a corresponding derivative along this. So the corresponding derivative to this is pi is delta f2 by delta qi, and qi is delta f2 by delta pi. So I have this f2. If I suppose that the generating function this is my f2, and that the corresponding derivative for that is going to be pi and qi, then I can write this equation as I can write h. For this h, I can write this, which depends upon q, which depends upon qi, and then I have pi. So pi here is my delta f2 by delta qi, and this is time t, and this is plus this delta f2 by delta t equal to 0. So this is one equation. This is my equation, and this equation, if I solve this equation, what I'm going to get is, if I solve this differential equation, this is the first order partial differential equation, then what I'm going to get is, what is my f2? Solving, I'm going to get this. Solving this differential equation, I'm going to get this, and this f2 is coming out to be what f2 it comes in our Hamilton-Jacobi theorem is known as, is defined as s, which is known as the Hamilton character principal function. Okay, so in effective, what you do is you write a generating function. You have this equation, and then you solve from this differential equation. You have when you solve this differential equation, you get what is the form of f2, and that form f2 basically, now this is going to be the generating function, and this generating function is in this case, like, is going to be defined as s in Hamilton-Jacobi theory, and that depends upon the q, and this capital P, because this is going to be is as f2 type. So, and then this is depending upon capital P, but this capital P is here is a constant, because we demand that the new Hamiltonian is going to be cyclic. So this is you define that this is P dot is 0, so that implies that this P is constant. Say this constant is some alpha, so this I can say this is alpha and t. So my solution that which f2 comes out to be is nothing but this function f, which depends upon coordinate and some constant and time t, that is so because this is constant, so I can write this as qt. So this is what is called as the Hamilton principal function. Okay, so in general, I can write the equation. The first order differential equation is like this in the Hamiltonian, which depends upon q. If my generating function is now this s, then this if you compare with this f2 generating function, this is going to have the corresponding partial derivatives, that this is pi and capital qi, as in case of you see, if you compare with this f2 type generating function, and then this equation is known as the Hamilton-Jacobi equation. Okay. is Hamilton-Jacobi equation. This is a first order partial differential equation, and the solution of this is going to give you the S, and that S is known as the Hamilton principal function. So once you know by solving this equation, what you're going to get, you're going to get a function which is the Hamilton principal function, and this function is known to have the complete motion of the system, information of the motion of the system, that can be obtained by differentiation, and we no need to solve the Hamilton entire equation directly, 2n equations of motion, because we already know that when you demand in Hamilton-Jacobi equation, when you write the Hamilton-Jacobi equation, your process demands that this pi is going to be constant, and then this small pi can be calculated from this Hamilton principal function delta S upon delta Qi, and the capital Qi is also is going to be constant, because you see that the p dot equal to 0, q dot equal to 0. From this I have this p is constant, and from here I have this q constant, which is also some constant. This is beta. Okay, this is alpha and beta, these are the two constants. So once you know this principal function, that is going to give you all the information. That's why I've written that is Hamilton-Jacobi theory that aims to simplify these equations of motion by finding a single function whose derivative contains the information about all the dynamics of the system. So this function is going to be the Hamilton principal function. So this is what the first aim of the Hamilton-Jacobi theorem. And what is the physical significance of that Hamilton principal function? So if you see that my principal function depends upon the q, that is second is the p, and that is the constant, and then time. If you take the total time derivative of this function ds by dt, so this is because this depends upon q, so ds with respect to q, and then dq by dt, and this is going to be q dot, because I'm differentiating with respect to t, and then it depends upon p, then dp by dt, that is p dot, and this is ds by dt. But this is going to be 0, because this term is going to be 0, because we demand in Hamilton-Jacobi theorem that p dot is 0. So we have the first term and the last term as a surviving. So this is what we have. Then what I have is from this theory, that k equal to h plus ds by dt we have, but because this is 0, so I have h plus ds by dt equal to 0. So h plus ds by dt equal to 0, and from here is ds by dt is minus of this Hamiltonian. And also when we know this Hamilton principal function, we can define this ds by dq is pi, and because we have in here ds by dq, this is going to be my pi, because if we say that from here ds by dq is pi, so this becomes pi q dot and then ds by dt. So I have ds by qi, this becomes pi, and then q dot is here, and then ds by dt is from this relation is going to be the Hamiltonian, and we know that this whole relation is defined as the Lagrangian of the system. Okay, so we have ds by dt, this total time derivative of the Hamilton principal function is my Lagrangian. So if I integrate it, if you integrate it, this is what I'm going to get is s is nothing but a Lagrangian plus some constant of integration. So the Hamilton principal function differs at most from the time integral of this Lagrangian, that is the time integral of the Lagrangian. This has to be careful about by this only constant. This is time integral and then some constant. Okay. So you will ask that why cannot we have a Lagrangian and take the time integral of that Lagrangian plus some constant of integration, that will give me that particular function, Hamilton principal function. But you cannot do this, because you cannot integrate the Lagrangian with respect to time, because the Lagrangian is going to depend upon this generalized coordinate and the velocity. So unless and until you know these quantity as a function of time, that is until the problem is solved. So beforehand you don't know this. Okay, so this is why in Hamilton-Jacobi theory you need that the transformation of the system when your Hamiltonian is depending upon time. So that is why it is not possible to calculate your Hamilton principal function by just integrating your Lagrangian with respect to time. Okay, so the if physically your Hamilton principal function is nothing but the time integral of the Lagrangian of the system plus some constant of integration. Okay, so till now, what we have did is like we have the theory and transform that theory, demanding that your Hamiltonian is going to be the simplest Hamiltonian, and that demands that your the coordinates are going to be the cyclic, and that is q and p are going to be the constant, and then you get a function, one function, the solution of the Hamilton-Jacobi theorem, one function that contains all the information about the dynamics of the system. Now moving further, if your system, if the solution of the Hamilton-Jacobi equation you are going to do is for the conservative system, when it is going to be Hamiltonian is a conservative system, is a constant of motion, that h does not depend explicitly on time. So that means delta h upon delta t is going to be zero, not depending upon time explicitly. So in this case, as you know that the general form of the Hamilton-Jacobi theory or equation is h. This is how you write the Hamilton-Jacobi equation as given in equation 1. Okay, this is my Hamilton principal function. But for conservative system, you know that h is a constant of motion, that h does not explicitly depends upon time. So what we have is this is takes the form. This is because here you have a time dependent on the Hamiltonian, but if you get rid of this time, so we don't have time here, so you see that is equal to 0. So when you have this equal to minus of this, so you see that I have a left hand part and a right hand part. So you see that the left hand part is completely depending upon the coordinate independent of the time, and the right hand is depending upon time. So we have separated the time dependent and time independent part, and they both are equal. We have a function which is one side is depending upon time and the other side equality, which is not depending upon time, but these two are equal. So we can in principle equate these two as a single constant, and that constant is going to be my energy, because we're talking about the Hamiltonian, and that constant is going to be energy, because h, because when h is conservative, then h is going to be constant of motion, and in that case we know that when h is conservative, constant of motion, that is always going to be the total energy of the system. So this part this part and this part were individually independent and depending upon time, but they were equal to that, so then we can equate them as a single same constant, that is going to be the energy of the system. Okay, so when we have this, so I can integrate this, so that on ds and dt. So this is what I'm going to get is from here I'm going to get this f, and this quantity is this quantity you get et, and some, if you say some constant of integration, that is my wp, which is known as the Hamilton characteristic function. Okay, so this equation that has two part, one is the time independent and the other is the time dependent part. So what is this is time independent part, and this is time dependent part. So the time independent function which is integration constant is known as the Hamilton characteristic function. Okay, so now this is Hamilton principal function, s is Hamilton principal function, this is Hamilton characteristic function, and this is, so my function which was for the Hamiltonian was not conservative, not for the conservative system, when it was dealing with time explicitly depending on time, then I was having a function that was known as the Hamilton principal function. This is s, which depends upon time. So when that contains all the information about the system, but when your Hamiltonian is for conservative system, is independent of time, then that can be separated into two parts. That is, one is independent of time and this is W, which is known as the Hamilton characteristics function, and one is time dependent path, which is ET. Okay, so now using this this is the final equation that contains the time independent Hamilton-Jacobi equation in terms of the Hamilton characteristics function. Okay, so earlier when you have this thing, you add here, that is delta S by delta T, and in place of this you have delta S by delta Qi, and you have T, so you have the time dependent Hamilton-Jacobi equation that was in terms of this S, the Hamilton characteristic function. But when the Hamiltonian is time independent, so then you have the Hamilton-Jacobi equation is written as like this in terms of the Hamilton characteristic function. Okay, so when I differentiate this with respect to coordinate, then what I'm going to get is only this part, because this is not depending upon time. So these two are equal when you talk about in terms of the position coordinate time independent part. Okay, so since this Hamilton characteristic function does not involve time, so the original and the new Hamiltonian are going to be equal, because these k is h plus ds by uh, df by dt. Okay, so when this does not involve time, the original, because that is going to be in terms of the generator, and that generator is going to be S, and that is in terms of W and T. Okay, so when this is not depending upon time, when in terms of W, so this part is going to be 0. So I am going to have the old Hamiltonian and new Hamiltonian is going to be equal, and because this is for conservative system, and then that's definitely they are going to be equal to the total energy of the system. Okay, so the Hamilton characteristic function thus generate a canonical transformation in which all the new coordinates are going to be cyclic. So once I know this S or W, Hamilton principal function or Hamilton characteristic function, so I can have the solution that is in terms of this Pi and Qi, because S is here in case of the type 2 equation of motion, and the same way the time independent part, that is going to be S is going to be as same as the W, except with the time dependent part. Then I can also have, if you know the W, the Hamilton characteristic function, then also you know the dynamics information about the dynamics of the system. Okay, and uh, we can see that what is the significance of the Hamilton, as you see that the physical significance of the characteristic function, that was some L uh, time integral of the Lagrangian plus some constant of motion. Okay, but we cannot calculate this. So in the same way, let us try to look into what is the physical significance of the Hamilton characteristic function, that is my W, which depends upon Q. This is constant and it's not depending upon time. So if I take the time derivative of this, so from here I am going to get Q dot, and from here I am going to get P dot, but this is going to be 0, because capital Pi dot is going to be 0. So I just have one coordinate, and this you see that delta W by delta Qi is going to be P here. So that is going to be PQ dot. Okay, so nothing but we have PQ dot here. Okay, and then if I integrate this, from dw to some or I integrate it, this is pq dot, this is dt. So if I integrate this, what I'm going to get is this is going to be dq by dt, and then I have dt and p, so this will cancel out. I'm going to have p times dq. Okay, so this is W. Now I know that S is the time integral of the Lagrangian, and the Lagrangian is written in terms of the PQ and H. This is how we define the Lagrangian of a system in terms of the Hamiltonian, because Hamiltonian is a sum over PQ dot minus L. So L from here I have going to be L is sum P Q dot minus H. So this is how you define the Lagrangian. So this is my Lagrangian, but you see in this Lagrangian what I have is P, Qi and dt, and then the second part is S dt. And this is what this is if you see that this is And this is nothing but my Hamilton characteristic function. And then I have this h dt. Okay, this is what I have. S is equal to w minus s dt. Okay, so since we have this relation between principal function and the characteristic function, then the time derivative of the Hamiltonian of the system. But the characteristic function comes into play when your system, the Hamiltonian, is not explicitly depending upon time. So this integral is going to give me et, okay, some constant, because h is constant in time. So that is h is going to be some constant, that is going to be e, and then this is that means this is some constant time dt. So what you get is e dt. Okay, so because h is a constant in for conservative system, then only then v comes into play, w comes into play. So therefore this characteristic principal function and the characteristic function, and then you have et. Okay, so this is what these now you know that how this principal function and the characteristic function are related with each other as compared to the time dependent and time independent part. So I'll stop here, and in the next class we will try to solve uh, one or two example, especially uh, for free particle. And if you see that for free particle, and then we'll go for the harmonic oscillator problem based on this Hamilton-Jacobi formula. So for now, I thank you all. Thank you.